Assalamu alaikum. I welcome all of you to the course on reactive intermediate. Today we will be studying reactions of carbenes. So let me review. In first lecture we just studied that what is the structure of carbene and how many type of spin systems of carbenes are possible. I mean to say that it has two spin states, singlet ground state and triplet ground state. So carbene can exist in both states according to their structure and the functionality attached to the carbenes. So today we will be studying the reactions of carbenes. So there are two main type of the reactions of carbene. Number one, insertion reaction, and addition reaction. Now let's move to the addition reaction and insertion reaction. Before discussing that, let me tell you one thing, that all the reactions of the carbenes depend upon its spin state, whether it is singlet or whether it is triplet. I mean to say that whether it is reacting in a singlet state or in a triplet state. So our main focus will be the state of the carbene and its reaction with the substrate. So let's first of all let's see that how the dihalocarbenes react with the alkene. First of all, as you know that how they are produced, this is a chloroform and simple alpha elimination will produce the carbene. There is a purpose that I am repeating this mechanism and you will know it. Now, as you see that this bond, it was composed of, it is a covalent bond, it's composed of two electrons, and both electrons in this covalent bond were parallel to each other. Paired with each other. One was up and the other was in down direction. So as the proton was abstracted, both these electrons sits on the carbon as such, and the spin is conserved. Both are now again they are in pair. So after that, this is intermediate. This intermediate can also go can also further decomposes to produce the carbene. So it again decomposes and produces a carbene. This is a dichloro or dihalocarbene. As you see that the spin of the spin of the bond is conserved. I mean to say that what was both electrons were paired in the bond and now both are again paired on the carbon atom. So majority of the carbenes, as they are produced, their spin is conserved. I mean to say that almost all the carbenes are produced in a singlet state. Now, as you know that the halocarbene, their ground state is also a singlet state, as it is produced in a singlet state, so it will remain in a singlet state. So its all reaction will be in a singlet state. What about the other carbenes? So we will be discussing that too. Now, as this carbene is produced, it will react with alkene. Suppose this is an alkene and it is cis. Now it is a cis alkene, and we want to react that dihalocarбine with it, dichlorocarbene, which was produced in the reaction I discussed previously. So its shape is like this. It was produced in a singlet state. The orbital was empty, and this is one chlorine, and this is the other chlorine. Pardon me for this mess. Now what will happen? Both these electrons, they just attack this carbon, and both the electrons in this pi bond shifts to this p orbital, and in the meanwhile the hybridization of this carbon changes to sp cubed or sp3. But as you see, that this is a concerted reaction. Now what is a concerted reaction? It's concerted reaction means that it just occurred in a single step. It's just occurred like this. So there was no chance for these methyls to move or rotate, and the stereochemistry of the product remained the same as it. The product is again cis, and Cl and Cl. So it is a concerted reaction. This means that the triplets or the singlet carbene always do or always does concerted reactions, but the triplet carbene will not do a concerted reaction, and because they are a sort of a bi or diaradical, and it will be clear to you right now. Triplet state of the carbene react differently in a stepwise fashion. It is not concerted because the triplet carbene is diaradical or biradical. As like this, suppose let me give you an example. Suppose this is CH2 double bond N, and this thing is heated, and it quickly produced a carbene. But this carbene, as it is produced, the spin should be conserved, and it should be first in a singlet state. Let me write it. And after a while, it will achieve its stabilized state, which is the triplet state. This is the triplet state. Look like this one, as I mentioned in the earlier. This is the triplet state. Okay. So it's triplet. Now if we want to react this triplet state carbene with an alkene, how will it add to the alkene? So it will act in a stepwise fashion, because it is biradical. From a biradical I mean that both these are like radicals, unpaired electrons. So let me draw an alkene. This is an alkene. So now I have tried a little bit stereochemistry with the alkene. This is CH3, and this is H. This is CH3, this is H. Okay, so this means that the alkene is present like this. This is the alkene, this is the H toward us, this one, this is another H toward us. Those CH3s are on the back side. It's a cis alkene, it could be written in this way too. Now what about the carbene? This carbene, if it wants to react with this alkene. So look, let's see. it is triplet state, so both the electrons have the same spins, but they are in separate orbital. But what about this bond? As you know that when a bond, in each and every covalent bond, the electrons are spin paired, so I have to write it in a paired fashion, like this one. I'm sorry. Okay, now these are in a paired fashion. Let me bold it now that it should be clearly visible to you people. Okay, now what happens? This electron and this electron, they are in opposite direction, and immediately they can produce a bond. So let me write it like it will produce its these fish hooks, arrows are for a single electron transfer or movement, so they form a bond. Now let's see that they have formed a bond, and the hybridization of this thing will change. It was sp squared, but now this p orbital is involved in a bond, and this molecule will become sp cubed. Look at this thing. Again, the CH3 is on the back side. This H is here, and now suddenly the CH2 has made a bond, and its electron is still up. Now, what about this thing? It is again like this. C3 is this. Let's say that there is nothing has happened to this molecule as yet. And what about this electron? As you see that its spin is again up. Now, no covalent bond is produced when both the spins of the electrons are up. So, either this electron or this electron has to change its spin in order to form bond. Either this should become like this, or this should become like this in order to be spin paired. And as these flips, both electron become as either electron flips, if it flips down or if it flips down, so immediately a bond is produced. But now another problem arises. This was a double bond first, a pi bond. So a pi bond, and you know that it is quite the pi bond, the electrons cannot, the carbon cannot rotate. But now it's a single bond, and now the bond can rotate. Again, now the bond can rotate, and the spin can also flip. The spin flipping is a little bit slower process, because it occurs only when one molecule collides with the other molecule, and the spin will flip down. Either this one will spin down or this one will be spinning down. So we don't care. And if any one of them is spin down or becomes an opposite spin to the other one, a bond will be formed. But what about the free rotation? Now we have another phenomena, a beautiful phenomenon. Free rotation across this bond is taking place, and the free rotation is much faster than the spin flipping, so the molecule will rotate. Let's consider that this part of the molecule is frozen and this one is spinning. So what will happen? This molecule will spin. I should write this as such. Now it is rotated, the molecule is rotated. This is CH3, and this is our beautiful H, and this is the carbon. But now the methyl was on that side, and the red one, suppose the red one is hydrogen, it is on our side, and the methyl was on the back side. What will happen? It will shift. Now in this case, the methyl will come here, and the hydrogen will move there. And let's say that it has its spin like this, and its spin is also like this. Now so this free rotation will occur unless and until the spin of the molecule is changed. So it can occur, maybe it can occur 10 times, 15 times or 8 times for a spin to change, because the spin change is a slower process and rotation is faster. So as the spin change, no matter if the molecule is in this state, the methyl on that side and the hydrogen on our side, or in that state, the methyl toward us and the hydrogen on that side, as the spin flip, the molecule will form a covalent bond. Let's say the spin flips. So immediately a bond is formed. And let's say here, again the spin flips. Why I am doing like this? Because there are two chances. The molecule can rotate in many rotation can occur. Say the molecule was in this rotation and the spin flips, and after some time the molecule come to this rotation and the spin again flip. Wow, a bond is produced. So as you see, let's set A and this one as B. So what happens? Two cyclopropane rings are produced. And how to write them? This is the one, A. Both the hydrogens are on the back side. Sorry, methyl. It is a cis one. And hydrogen on all sides. This is a cis. And the B, this is A. Let me write A inside it. And this one is the B. Now one CH3 is like this and the other CH3 is like this. One on the back side and the other on the front side. You can also draw the hydrogens. This hydrogen in the front side, this hydrogen in the back side. So statistically, two products are produced just because of the free rotation. So the triplet carbene, as it reacts in a stepwise fashion, so it gives the time as it breaks the bond, the double bond, so it's give the time to the molecule to free rotate till it will be rotating till the spin flips, and no one knows that whether the molecule will be in this form, in this stereochemistry or in that stereochemistry when the spin flip occur. But statistically, both the products are equally formed, produced in an equal amount. So both are produced in an equal amount. Ratio about almost, if that was our example, let's suppose this was a cis alkene and it is reacted with a triplet carbene. So it will produce both the products. Okay. Or if you want to understand it a little more, so I can write it like this. S, okay, My drawing is very bad, but I will still try. Look at this. Suppose one methyl is up and the other methyl is down. So here hydrogen is down and here hydrogen is up. And in this case both are up. This hydrogen is up and this methyl is up and this methyl is up. So I think that maybe you can understand it. And this can also be written like this. This is a trans one. No matter what isomer you take, you will meet with both the cis and the trans. Suppose now you take this isomer. Now this is a trans. Again you want to react it with the triplet carbene. The result will be the same. Oh God, help me to draw this correctly. Almost in 50-50 ratios. So this is how the triplet carbene reacts with the alkenes, and it's called as the non-concerted reaction or a biradical reaction. So